This is a tutorial on parametric equations. Parametric equations are just equations that we create that describe an xy equation. We make parametric equations a lot when we deal with conic sections, because there are many conic sections that are not functions. Here I have the graph of a parabola. Notice that if I use the vertical line test, that this is not a function because I intersect my graph in two places. Now if I were to write the equation of this parabola as y is a function of x, then I would find it very difficult to find both of these points on our parabola. Again, because this is not a function. So what we do is we create two functions called parametric equations. One of these functions describes the x coordinates of every point on this line, and the other equation describes the y coordinate of every point on this line. And these two equations are functions of some other variable. And usually when we deal with parametric equations, we make that variable t. So instead of using the function equation for this parabola, we instead use two different equations where our x value is some function of this variable t, and our y variable is equal to some function of that same variable t. Another way to think of this, and this is why we frequently use t when we have a parametric equation, is that if I started here at time 0 and I walked in this direction, as time went by, I would have a different x and y coordinate. So my x coordinate and my y coordinate would be a function of what time it was as I walked along this parabola. So here are the parametric equations for this parabola. And notice that our t is restricted between -4 and 4. But if I plug in a value of t, say 0, into both of these equations, I would end up with an xy coordinate. And that x and y coordinate would be on this parabola. So let's try doing this and see how this works. I'm going to plug in values for t, like -4, -2, 0, 2, and 4. All these values are between -4 and 4. If I were to plug in -4 in for t into my x equation, I would have -4 squared, which is 16, and then multiply that by 1/2 and I would get 8. If I plugged in -2 for t into this x equation, I would end up with -2 squared, which is 4, multiply that by 1/2 and I would get 2. If I plugged in 0 for t, I would have 0 squared, which is 0, multiply that by 1/2, and that's still 0, so my x coordinate would be 0. If I plugged in a +2, I would square that. I would have 4, multiply it by 1/2, and I'd be back to 2. And if I plugged in +4 for t, I would have 16, multiply that by 1/2, and I would end up with 8. Now let's do the same thing for our y parametric equation. If I plug in -4 for t, I'd have -4 times 2, that's -8. If I plug in -2 for t, I'd have -2 times 2, and that would be -4. If I plugged in 0, I'd have 0 times 2, so that would be 0. And if I plugged in a +2, I'd have 2 times 2, and that's 4. And then if I plugged in 4 for t, I'd have 2 times 4, and that's 8. So now I'm going to plot these xy coordinates. At t is equal to -4, I'm at 8, -8. That is right here in the corner of our graph. At t is equal to -2, I'm at the point 2, -4. That would be right here. 0, I'm at 0, 0. That's right here. At t is equal to 2, I would be at the coordinate 2, 4. That would be right here. And then at t is equal to 4, I'd be at 8, 8, which is way up here. So I am moving in this direction, or you can say my orientation is in this direction. So as my value of t changes between -4 and 4, I'm moving in this direction along my parabola. And these are the parametric equations for my parabola. So now let's try converting from a parametric equation back into an x and y equation. Here I have the same parametric equations that I did before. And the easiest way to do this is to take the simplest equation and solve it for t. So I'm going to use this y equation, and I'm going to say t is equal to y over 2. Then I'm going to plug this back into my other equation for t. So if I do that, I'll have x is equal to 1/2 times y over 2 squared. This will simplify. I'll have x is equal to 1/2 times y squared over 4. And my equation then would be x is equal to y squared over 8. Or I can multiply both sides by 8 and I'll have y squared is equal to 8x. So this is my xy equation for this parabola. Remember that my domain is restricted, which means my domain is going to be restricted for this equation as well. If you think back to when we plugged in all those different values of t into these two parametric equations, we know that the domain is that x has to be between 0 and 8. Now let's work on another example of converting a parametric equation. Here we have x is equal to 7 times the cosine of t and y is equal to 10 times the sine of t. Now whenever you have parametric equations that involve cosine and sine, usually the easiest way to convert these into an xy equation is to use the trig identity, where the sine squared of whatever angle plus the cosine squared of that same angle, that's always equal to 1. So what I want to do is take these two parametric equations and rearrange them so I have the cosine of t is equal to x over 7, and then the sine of t is equal to y over 10. Once I've rearranged these two equations, I just plug in for cosine t and sine t into this equation. I'll end up with x over 7 squared plus y over 10 squared is equal to 1. Now you can square the numerator and the denominator for both of these. So we'll have x squared over 49 plus y squared over 100 is equal to 1. I have eliminated all the t's out of my equation here. This is the equation of an ellipse. And this would be my xy equation that's derived from these two parametric equations. Now sometimes we're asked to create a parametric equation from an x and y equation. Now you have to realize that there's several right answers when we do this. Because the way to do this is just to take your x variable or your y variable and set it equal to some equation with t. The easiest being x is equal to t. So I found one of my parametric equations. To find the other one, I just plug in t for x. So I'd end up with t squared over 16 plus y squared over 1 is equal to 1. Now I solve this for y, so I'll have y squared is equal to 1 minus t squared over 16, and y is equal to the square root of 1 minus t squared over 16. So those would be two parametric equations that represent this x and y equation. Now I could have also said that y was equal to t. And then I could have plugged that in. I would have had x squared over 16 plus t squared over 1 is equal to 1. And I could have solved this for x. I would have had x squared is equal to 16 times 1 minus t squared. And then I would have taken the square root of both sides, and I would end up with x is equal to 4 times the square root of 1 minus t squared. So here are two different parametric equations that also represent this rectangular coordinate equation. Sometimes we want to create parametric equations for the motion that an object takes. Here, we're walking around this circle. We're given the equation for the circle, x squared plus y squared is equal to 25. This is in the form of x squared plus y squared is equal to r squared, which means our radius here is 5. I'm told at time 0, I'm at this first point here. At time 2, I am at this point. And then at time 8, I'm back here again at my original point, 5, 0. Which means it takes a time of 8 to do one full revolution. Now what I want to do is create parametric equations for every point on this circle in terms of t. Well, if I'm at this point here, and this distance is 5, and this angle, I would say, is theta, that would mean that my x-coordinate would be this distance, and my y-coordinate would be this distance. So I would say x is equal to 5 times the cosine of theta. And y is equal to 5 times the sine of theta. Now if I chose a different point on my circle, say this point here, well then I could use the exact same x and y equations based on my new version of theta. So the only thing that changes as we go around this circle is the value of theta. My radius doesn't change, so it's still just 5 cosine theta and 5 sine theta. So the question is how does theta change as I go around a full rotation of this circle? Well, a full rotation of this circle is 360 degrees. And I do this over 8t, which means for every one value of t, I go 45 degrees. So instead I'm going to change these equations. I'm going to say x is equal to 5 times the cosine of 45t. But notice that I'm going in the negative angle direction, so I'm going to make this a negative 45t. And then I'm going to do the same thing for y. Y is equal to 5 times the sine of negative 45t. So as t changes, my x and y coordinate will change. So these would be my parametric equations for moving around this circle, which has a radius of 5, and at a rate of one full rotation every 8t, or every value of t that's equal to 8. Now a very common use for parametric equations is when we're trying to do problems involving projectile motion. Here we're told that an arrow is released from a longbow at a velocity of 200 feet per second and at an angle of 45 degrees from the ground. So use the given parametric equations to find out how far the arrow flies. Now if I tried to use an xy equation to mimic the flight of this arrow, then I would find it very difficult to find this x value, assuming that this here would be the origin of our y and x axis. Instead, we use these parametric equations. Here, x is equal to our initial velocity v naught, which is 200 feet per second, times the cosine of theta, which is 45 degrees, times t. This you can think of as the x component of our velocity. Our velocity is moving in this 45 degree direction, but this is the x part, or the amount of this 200 that's going in the x direction. And that means that this is the amount of our speed that's moving in the y direction. Now if you take your velocity or your speed and multiply it by time, you will get distance. So our arrow is going to go up in the air in the y direction and then back down until it hits the ground, which we say is when y is equal to 0. And what we want to know is this x distance. Well, let's take what we know. This y is equal to 0, and we're going to set this second parametric equation equal to 0 because y is equal to 0. So I'll have 0 is equal to, now v naught is 200 times the sine of 45 degrees, and then times t, and then minus 1/2 g. Now g is the acceleration due to gravity, and since we're dealing in feet, this is equal to 32 feet per second squared. But we'll just put 32 in there for now, and then times t squared. 200 sine 45, that's about 141.4, and that's still times t, and then minus 32 times 1/2, that's 16 t squared, and this is equal to 0. Now I can factor out a t from both of these, so I'll have 141.4 minus 16t all multiplied by t, and that's equal to 0. This is factored, which means t can be equal to 0. Or I can say that 141.4 minus 16t is equal to 0. And if you solve that for t, this will come out to be about 8.8. Well, we know at t is equal to 0 or time equal to 0, we would be at this point, which means this other point must be when t is equal to 8.8. So since we want that x coordinate, we're going to take this 8.8 and plug it into our first parametric equation for t. So that means x is equal to v naught, which is 200, times the cosine of theta, so the cosine of 45 degrees, and then it's multiplied by t, but we know that, that's 8.8. Plug all of this into your calculator, and that means x is equal to 1244, about 0.5. So if that's our x coordinate, and we said this one was 0, that means our arrow flew 1,244.5 feet. So by using parametric equations, we were able to solve for a y distance and then solve for an x distance, all by using these functions with time in them, or t in them. And that actually makes it easier to solve equations like this than using a standard x and y parabolic equation. Now that completes the tutorial on parametric equations.